Hello and welcome everyone to today's session, IMechE meeting on the present oil and future liquefied gas large-scale marine transfers. I will be your chair for this lunchtime's presentation. I am myself, Pamela Robinson. If we move on to the next slide. The plan is to run with the main presentation with Emily for about 40 minutes, and then we'll follow with a 20 minutes Q&A session. If you could post all your questions in the chat box, which is available in your overview box, which is off to the side. If you post all your questions there, we should be able to get to them at the end of the presentation. If there are too many, then we'll sort something out to be able to answer them later. So I mentioned myself, I'm Pamela Robinson. I currently work for United Utilities as a senior mechanical engineer. So I've got background in water and wastewater industry. Our speaker today, Emily Ho, if you can just give a brief introduction, please.
Hi, I am a chartered mechanical engineer. I am the project manager leading low temperature liquefied ammonia and liquefied carbon dioxide marine host development in Dunlop Oil Marine in Grimsby, UK.
Thank you, Emily. And then our two panel members, Richard Coe, if you can give a brief introduction, please.
Yes, good morning, everybody, or good afternoon, should I say. My name is Richard Coe. I'm chartered mechanical engineer and also a chartered quality professional. I'm a consultant in the pharmaceutical industry, but I'm hopefully bringing some expertise in safety of enclosed process systems to today's discussion. Thank you.
Maurice, please.
Hello, I am Maurice Worthington. I'm the Vice Chair of the IMechE Process Industry Division, Northwestern Centre. I'm a retired engineer, but I'm a chartered engineer and a fellow of the Institution of Mechanical Engineers. My role is a panel member for this presentation, given by Emily.
Thank you. So as mentioned before, any questions, please put them in the chat box and we'll get to them at the end of the presentation. Now, Emily, over to you to deliver today's talk. Thank you.
Hi, good afternoon, everyone. Thank you for joining us today. The energy sector is currently going through a transition period. On one hand, we are supplying oil and gas responsibly, reliably, and affordably. On the other hand, we must work towards a net zero future. I'm here to present to you our ongoing development in the different fields with large-scale marine transportations. This is an insight of a little part. This is an insight to a little part of a much bigger industry serving all of us daily. First of all, I shall quickly introduce Dunlop Oil Marine, then describe the current oil transfer operation in demanding marine environment, and share with you the exciting development of new hoses for the global new energy market. Dunlop Oil Marine is a manufacturer of marine hoses for oil transfer worldwide. We're based in Grimsby, the east coast of England, and have approximately 250 employees. Marine hose string can be floating or submarine. can be floating or submarine. Hundreds of meters long in each systems. They have been used to transfer oil offshore and near ports. Our Grimsby plant was built in 1955 and started making hoses in 1958. We have a strong focus on providing quality products. Our flexible manufacturing processes enable tailored solutions to all our customers. We also provide a full scale of customer support and services. Dunlop Oil Marine Ltd is part of the ContiTech group of Continental. We therefore have access to a wide range of specialized material technology and knowledge. Oil and gas is everywhere, supporting our daily life. We use it as fuel, lubricants, coatings, as well as feedstock for fertilizers, road building, waterproof, and lightweight materials. They enable us and empower us to many activities, functions, and comforts. According to a survey in 2016, an average globally, 0.5 gallon of oil is consumed per person per day. And from a Clarkson's 2022 report, 17% of natural gas and 64% of oil produced globally moved by ship. So, how are oil and gas being transported by sea? From offshore to onshore facility in relatively calm, protected, and shallow bay area, conventional buoy mooring systems are used. The submarine hose sit on the normally connected to the pipeline and manifold pump and lay on the seabed. It is picked up on board for offloading when a tanker arrives. In deeper and rougher sea locations, single-point mooring systems are used. Floating hose deliver oil from the tanker to the buoy, and then submarine hose transfer it from the buoy to the fixed pipeline on the seabed, which is connected to our onshore facility. These marine hoses stay in the sea throughout their service life, 5 years, 10 years, or even 15 years. They have to withstand the element of the ocean, wave, tide, wind, temperature, even hurricanes and earthquakes. Marine hose also offload oil from floating production facilities to tanker. So floating production facility typically stay in remote or deep water location where fixed platforms are not suitable. This is an example of a single moil boring system. Oil is transferred from the tanker through the floating hose to the boil, and then by submarine hose to the pipe end manifolds, to an offshore pipeline, and then an onshore pipeline to onshore facilities. The vessels stay in the boil swing circle while oil is being transferred. Here, this is an image of oil transferred from a folded production facility, storage and offloading unit to a shuttle tanker with a floating hose. It is, however, not all operation just same as before. Climate change means that our ocean environment are becoming more hostile. We are increasingly seeing single point mooring systems rather than conventional buoy systems. Our hulls are meeting higher specifications in strength and fatigue than ever before. Hydrostatic and hydrodynamic studies are carried out in the design stage to design a system that performs in the environment, to minimize forces in the system, and to define the hose reinforcements. The Oil Companies International Marine Forum, OCIMF, and the American Petroleum Industry, API, and other bodies, for example, in defense, have guidelines or standards on technical requirement and qualification tests for oil transfer. This hole on the left is being tensioned, torsioned, and cyclic bending. In the middle, the integrity of the hose connection will test. And the final full hose test was a burst to at least 5 times working pressures according to OCIMF before the hose are cut up for section inspections. For quality control, each order will undergo batch tests and certifications. Here are 2 of them. To the left, we can see the hose in our bend test rig performing the minimum bend radius, in which the hose was taken to 4 times its internal diameter. On the right, the marine hose was weighed in water after weighing in air. Technology is also now at the stage where we can do remote health monitoring of floating system through clever use of sensors. This can help to optimize offloading schedule, service periods, and system design. Full history available will enable machine learning, more timely actions in the future. As a marine hose manufacturer, we are regularly asked by customers as to what can be done with old hoses. So, a few years ago, we conducted a survey with marine hose users. And we got over 50 responses from around the world. Based on those responses and the market size, we estimate that there is about 10,000 tons of marine hose being retired from surface every year. And this is equivalent to the weight of 70 blue whales. The historic model for product consumption was to take raw materials, make the product, use the product, and then dispose the product. Start again. The Paris Climate Agreement and the drive for carbon neutral is challenging that historical model, and we need to find more sustainable way of consuming products. Now, the desire is to set up a circular economy type model, whereby products are reused, remade, or recycled rather than going to landfill. This is what manufacturers and customers have to work towards if we are to achieve carbon neutral in the coming decades. Another model I'm presenting is the waste hierarchy in terms of disposals in an environmental friendly manner. There is a preference to disposal, from reducing consumption through to sending to landfill. And I use this to discuss marine hose disposal options. So the most preferable options on the waste hierarchy is to reduce consumption of products using fewer marine hose. Well, it seems strange for a hose manufacturer to suggest using fewer hose, but I shall explain. There will be several lengths of hoses required in a system, but we can optimize the surface life of the hoses to be purchased, optimize the cycle time so that over a period, there will be fewer new hose purchased in the first place that at that point will need to be disposed of. How do we do that, you may ask? Some examples. Consider using API 17K hoses for subsea systems. 17K hoses are designed with greater capacity and longer fatigue lifetime, allowing much longer surface period before change out. Double carcass hoses. They have been around in our industry for years. But they provide the extra reassurance and risk reduction when seeking to optimize surface period for each floating hose positions. Or, and choose proven hoses with high quality and fatigue-resistant material. Look at the overall life cycle cost rather than initial purchase price. Also, remote health monitoring of voting system through clever use of sensors and digital technology. This can help optimize surface period and system design. The next best option is to reuse the hose. Can we find a second purpose for the hoses that have their surface period? These are a few common ones. There are, however, usually no reliable and regular markets for this use. Next on the hierarchy is repair. It is about keeping the hoses in surface. As per OCIMF recommendations, have a good maintenance inspection program for the hoses. To optimize hoses surface life, we recommend, if possible, that conditional-based assessment is followed rather than time-based. Access management software will also help to keep track of hose conditions and field test results. When hoses are finally retired from surface and can't find a second use for them, we consider ways to recycle. Marine hoses are not easy items to deconstruct because of its composite, multiple layer structure. How do you do it? There are a number of technologies employed for recycling tires, and some of them are applicable for marine hoses. The two showing most promise for marine hose application are mechanical and thermal. Mechanical can include cutting, tearing, shedding, and jetting. Thermal cover techniques like pyrolysis. Unfortunately, the makeup of the hose will require a number of these processes to break down one single hose into its constituent parts that can potentially be reused into other products. There is the next problem. Finding an outlet market for the deconstructed materials. Steel is relatively easy. The others, not so. Last, we look at burning the hoses. As the carcass, similar to tires, have high calorific contents. They can generate heat and power. The pyrolysis technique can recover the carbon back from the rubber compound and recover oil and gases, leaving the steel component to be recycled. And yet, much more changes are happening for the longer term. We can be shipping more and more liquefied gases than oil-based product. They can be transported from shore to sea instead of from sea to shore. Looking at the trend in the energy market, oil demand is to peak in 2029, while natural gas is to maintain for some time. Providing decarbonizations across industry, the renewable sector is growing fast, which presents challenges but also opportunities. Green sources of energy are being sung, and hydrogen is being considered as a clean source. Then, transportation challenge with hydrogen results in interest in ammonia. The pressure to decarbonize is also generating a market for carbon dioxide to be captured and stored. The idea of carbon capture and storage is to collect the carbon emission from major industrial sites, compress and cool them in liquid, and then transport them by pipeline or ship to offshore locations. Then they are injected into deployed oil and gas field or aquifers. Gigatons per year of carbon dioxide will therefore be taken out of the Earth's atmosphere. A large-scale carbon capture and storage is still at an early stage of development, but the International Energy Agency are saying that it will be virtually impossible to meet global climate targets without using this technology. The scale-up and knowledge, effective techniques and equipment developed over decades in the oil, gas, and chemical industry are most closely related to carbon capture. We are now actively leading the development. Last year, the UK government selected the East Coast Carbon Capture, Utilisation and Storage Industrial Cutter in Loughton, England, as one of the two to be set up and running by mid-2020s. Another two more clusters will be running in UK by 2030. Meanwhile, hydrogen and ammonia are projected to be the important green field in 2050. Hydrogen is generated from water electrolysis using green energy from wind, solar, or hydropower, and ammonia acts as a carrier of green hydrogen. We have a lot to do to realize it. Our industry and government are investing and pushing the development of technology and infrastructure. Ammonia is easier to transport in liquid form as dense hydrogen requires either very high pressures or very, very cold temperatures. The carbon capture and storage industry is planning to use marine hulls to transfer liquefied carbon dioxide from the transport tanker to the deployed offshore reservoir for storage. So interests are growing in the market for marine hulls for both ammonia transfer and the transfer of liquefied carbon dioxide. They are expected to be hundreds of meters long as oil marine hoses, withstanding the element of the ocean throughout their surface life. New hose material compatible to liquefy ammonia and carbon dioxide, and new hose construction that minimize conversion back to ingress are required. There are many design and operating requirements for liquefied gas hoses that are different from hoses designed for handling cool oil or liquefied petroleum products. As highlighted in Gun Form 2009, liquefied gas are kept at low temperatures with high formation risks. It is subject to temperature and pressure cycles. When the temperature increases, they permeate and expand readily. The guidelines, however, do not specify the method to quantify the performance. There are currently no standard for liquefied carbon dioxide hoses, and ISO 5771 can only be applicable to small bore ammonia hose less than 3 inches. Ammonia is toxic and currently restricted as a marine fuel. Liquefied carbon dioxide hose will be rated for 40 bar, while oil marine hose are normally 21 bars. For liquefied gas, it can have phase change and expand. So a can of liquefied ammonia can turn to ammonia gas enough to fill a barrel, a drum, at minus 33 degrees C. It can happen very quickly if there is a good supply of thermal energy and cause rubber blister and damages. Phase change, therefore, must be mitigated and controlled in liquefied gas applications. While there is very small amount of liquid changing phase, we relied on the composite pile structure to restrict the internal expansions. The liner material is critical in limiting the fluid concentration inside the whole composite structure, because any outer layer in the structure cannot have a higher concentration than the liner. Fluid can only move from high concentration to a lower concentration, while the rubber still provides flexibility to cope with the dynamic marine conditions. We know that it will be more and more challenging and demanding as bore size increases. We utilize our decades of know-how on marine hose structure strength requirement and large bore composite pile structure on the new designs. To give ourselves and our customer the confidence, we have to test our hose material and design in representative conditions. The only option is to therefore to have our own test unit installed and run in our Grimsby site at the back of the factory. It composed of a tech room housing the refrigeration unit and an ATEX room housing 7 test vessels. Just outside the ATEX room are the liquefied gas supply cylinder. Then the test vessel will be remotely monitored and operated in the control room. We have multiple test jigs designed for different testment: rubber physical properties, reinforcement coil, material to metal adhesion, and rubber permeation. There are also vapor gas expansion cycling jigs and composite power jigs. Each test vessel can be independently temperature controlled, start up and shut down. We aim to run all 7 test vessels at the same time, 24 hours, 7 days a week, to meet the customer's schedules. Like engineers everywhere in the industry, we have a busy time ahead for many years to come to enable green energy delivery to the world's population. Our marine host development program, therefore, complies of multiple teams working in parallel: material development, design, testing, stimulation, manufacturing techniques, economic of scale, quality control. They are all interlinked. Today, I have provided you with an insight to the advancing oil and gas operation and our ambition for the future. Marine infrastructure has been successfully moving oil across oceans for many decades. We want to do the same for the future green fields: large-scale, safe and durable, low-temperature, pressurized transportation. There is a climate emergency. Still, we must get everything right. We are approaching the challenges with innovation in engineering and science, material and manufacturing techniques. We invest in leading-edge test facility, our people, and our knowledge. We utilize our expertise, our experience, explore new options, and learn from other industry. Engineers are therefore working tirelessly to cover all aspects required for achieving a less zero future. And thank you for your attention.
Thank you, Emily, for that. Sorry, on the screen now are some links for your CPD certificate, should you wish to get one of those, and any event feedback. This presentation will be sent out later, so you'll get a copy of this if you don't quite manage to jot down those notes. If you can go to the next slide, Emily. Just like to draw your attention to the next event that we are hosting. It's on energy transition, geothermal energy opportunities and barriers, and it's a tech talk on the 30th of November, another lunchtime webinar. If you're interested in that, please go to the Near You website, IMechE website, and register your attendance there. So thank you very much for that, Emily. We'll now open up to the questions. We've had a few in. So what the first question that came in, what level of internal pressures and temperatures are your hoses rated to? Which I think you did answer later on, Emily.
Sorry, hold on. Let me just stop sharing first. So.
Sorry.
Yes. What's the question?
If we can have the other panel members as well on the screen, if they can make themselves visible, that'd be appreciated. Sorry. So Emily, what levels of internal pressures and temperatures are your hoses rated to?
We are rated to for for carbon dioxide, for liquefied carbon dioxide is 40 bar and minus 50 degrees C, down to minus 50 degrees C. For the ammonia is 25 bar and down to minus 33 degrees C.
Thank you. But that's more than what it is, what they're currently rated to. Now I got from your presentation.
Yes, that is more than, the pressure is higher than what we normally use now, which is 21 bar, and we do not normally go down to minus 50 degrees C. No.
Thank you. Also asking the material of your hoses. I'm not sure if you divulged to be able to tell us the material. It mentioned something about top secret on your slides.
The material, we have rubber, rubber liner, which is a barrier liner, so it won't allow ammonia or carbon dioxide to go into the inner part of the hose. And then the subsequent, there will be a layer of reinforcement to make sure that it can still fatigue. We can still handle fatigue and tensile and torsion. We have embed spinal wire for to withstand crush, internal outside crush. And then we have many layers of rubber, and most of them, to achieve the dynamic capability, they are they're composed of lateral rubber. Lateral rubber is one of the most dynamic rubber at low temperatures. Yes. So it's a lot of different composed, a lot of different material, and that's why we face the problem when we try to recycling it, to take them apart again.
Yes, that leads us on to another question. Do you think in the future there will be the technology to allow hose composites to be recycled into new hoses, or perhaps even other purposes?
We at the moment, we've gone through the different recycle we use. We are looking at the moment is to recover carbon back, which can be used in other rubber industry with production, and also we're looking at the steel can be used readily. We use readily, but maybe with gas and oil extracted can be reused, but it is a limited part, and we are still ongoing development. We're spending loads of manpower onto the topic. Yes, and that is our aim, is to try to use as much as possible. That is our target, but yeah, we're working towards it.
Thank you. Given that the LNG transfer system is a compressed gas system of substantial volume and subject to the pressure equipment safety regulations 2016, but is technically exempt under Schedule 1, Clause 1A, how are the potentially significant residual safety concerns arising from this apparent blanket statement managed during design?
We marine hose, we work towards the PED, the Pressure Directive, and we have two standards. We have standard already, like the gun foam and the API and other defense standards that will require us to test the hose to at operating temperature, above operating temperatures, and burst test it to 5 times the operating pressures. So we have a full set of tests that need to be carried out to ensure that it is safe as a pressure, as any other pressure system.
Thank you. Richard, did you have anything further to add?
Yes, I think on that one, I was just sort of listening with great interest to your presentation, Emily, and the extensive testing and pressure testing and fatigue testing that you do, and I think that's admirable. I think my concern would be that, and in relation to the underlying message in the last question, would be that how this is managed as an industry as a whole. I think your company specifically, it sounds as though you're doing a large amount of very good work, but in relation to the industry that I work in, which is pharmaceuticals, we've had, similar safety concerns in the past, and obviously in pharmaceuticals, if there's an accident, then quite a few patients get harmed and so on, and that's resulted in our industry becoming highly regulated. So that, for example, going back to your question, you'll test and self-certify the individual lengths of hoses, but then how is that then captured in a controlled manner? Because I'd presume once you've sent that hose out for use in industry, then who looks after that and who makes sure that it's used as intended, and who retires it at the end of its intended life? I think that that's the sort of the inputs there.
For the oil marine hose, there is the standard, which is the gun form standard, the OCM IMF standard, and also the API standards, which we adhere to depending on the customer request. And so we will have those tests done with third party certified bodies, and it is common in our industry that if we quote it is API 17K hose, or if it is gun form hose, we have to provide certification on the test that we have performed, on the list of tests that is specified. The problem we have now is some of that doesn't have low temperature testing, doesn't have liquefied gas tests, cycling tests, and that was not relevant for the oil marine hose. So for that part, that's why we spend the whole year to design and build a rig that we can put our material and hose construction into a test rig in low temperature, hot pressurized, liquefied ammonia and liquefied carbon dioxide, to see that it is still reliable, good performance, intact material and structure before and after test, so it doesn't detect the material and the strength doesn't drop drastically because it has been in the low temperature or it has been subject to the new fluid. We do it our best to think what we believe is required, but there is no standard currently. There is little exactly what they got industrial agreement is on that front, and we are trying to do our best for what we think it is required. And as I say, we take the effort to spend a whole year to design and build the rig.
Yes, I think it's sort of a message to the to the industry generally, that I think, given the undoubted increased risks associated with compressed gases, and if we start to use these things for hydrogen transfer, for example, then that risk increases yet again. It would be really sensible for the industry to get together and produce some sort of self-regulation. And then you've got the additional risk that obviously if you sell your hoses to somebody as a system, then that somebody then also has a great responsibility to look after that system and operate it as intended. So, taking my pharma industry as an example, then I would prefer the regulation to lead the accident rather than the accident drive the regulation.
We do in the industry, we do have customer surveys. Because all marine hoses are made to order, so for us, we have a full record of when was it made, what material, which batch of material it is made, and then we would recommend it inspection after a certain period, or even sometimes for a whole strings of 20 hoses, bring one back up to us or to our agents for burst test to check that it's still reliable, and then you can extend it for another few years. So we do recommend, we don't just, it's not just like the hose is out of the factory and that is the end of the story. We do keep supporting our customer in maintaining make it last as long as possible. And we're working towards the waste disposal as well. And that is the general trend in the industry as well.
Yeah, well, I think that's admirable customer service and goes a long way to your customers dealing with their own health and safety risk assessments. Thank you.
Thank you. Have we got Maurice on the call? Oh, Maurice, we just can't see you, that's all. Did you have anything further to add on this particular topic?
No, I think I was going to ask about material certification and test certificates supplied to the client. I think Emily's answered those. She mentioned test certificates being supplied. I've just noticed the next question. I think I can deal with that.
Okay, yeah. Okay. Yeah, I can
Can't you see me?
No, we can't see you. Well, I personally can't see you. I'm not sure if anyone else can, but how do we, so the next question come in. Yes, I can see you now. Yes, right, thank you.
Yeah.
How do you ensure that boat transfer pumps cannot overpressure the hose in the event that the isolation valve between the hose and the bulk tank is inadvertently closed?
Yeah, I've had some experience designing this type of system. You've got to be careful with the velocities. I'm thinking of unloading from a boat to a storage tank on shore, and the problem is if the valve is shut off suddenly, there's hydraulic shock that goes back to the hose. So the isolation valve should close very slowly. I was thinking something like a slow closing butterfly valve, that type of thing. So the hydraulic shock is minimized. Also with the pumps, we've used sliding vane pumps to transfer from the ship to the hose along the pier. They don't lose suction. So I don't know if that answers the question.
Emily, did you have anything else to add to that question?
I think that there is the normal pressure for the liquefied gas hoses. Then there is the risk of rapid increase in pressure if the temperature increase rapidly. So for our hose, they are very well insulated. Otherwise, they won't be transporting liquefied gas material. So there will have be time. So if it is the thermal temperature, it should gradually relieve it will have a mechanism to gradually relieve the system pressure to avoid over pressurize it. But for ammonia, it is less of a risk because it is even at 50 degrees C, it is still something low at relatively low pressure, say 20 bar, whatever. But the carbon dioxide host can go up to 50 bar, even at 15 degrees C. So we do have to have a system that have to be very carefully designed, the whole system to relieve the pressure should it happen that the gas rapidly expand.
Thank you, Emily. Richard, did you have anything else further to add on this topic? You're on mute, Richard.
Oh, sorry. No, I think it just comes back to my sort of previous thoughts about just making sure that the system has safeguards in it that prevent the accident from happening. But also there's also then the concern that the operators need to make sure that those safety systems are functional and are operating as intended, before the system is put into use, perhaps sort of every time before the system's put into use. So that will be my concern there, that it comes back to having a sound set of operating procedures.
I think the oil and gas and chemical industry has a good knowledge and approach towards safety, how to minimize safety. I think the challenge for us is to get that all list out, agreed in the short period of time. In that is the time. Is our challenge is make it more problematic because we have such a short time to do the job. As you say, it is developed over the years with people from multiple organizations, knowledge of a wide field. Yeah.
I mean, I just cite Piper Alpha disaster, which was a clear case of the right hand not knowing what the left hand was doing, and and then what ensued was pretty disastrous. So that's the thing, we need to bear those sort of things in mind.
Thank you. Thank you. That'll draw a close to today's presentation. Thank you very much for Emily for her talk this lunchtime. I've learned a lot about the technology that you're doing, how the hoses you're trying to develop this circular economy, and then how the hoses can be used for other things. So you're looking at carbon capture and transfer of hydrogen. Very, very informative. Thank you very much for our additional panel members, Maurice and Richard, for your added contribution during the Q&A session. And I'll just remind you to look on the IMechE near you website for any future events. This recording will be posted in due course when it's ready, and from there you can gain your links to the CPD certificate. So thank you very much for your time this afternoon.